Hello everyone, welcome to the lecture 13. In this lecture, we're going to talk about groundwater table and the capillary pressure in the soil. So first, groundwater table. And groundwater table location is defined as the steady-state elevation of freestanding water in an excavated exploration hole. So all the steady-state elevation at which the pore water pressure is equal to the atmospheric pressure. So if you dig a hole deep into a soil, subsurface, and you meet the groundwater table, and when you meet it, then you'll see that freestanding water. So you'll see the clear water surface in the hole, and that's the location. And if it doesn't move, then that's the location of the groundwater table. So below that groundwater table, this groundwater table, you can assume that the soil is 100% saturated, and above it, it will have the degree of saturation less than 100%. So it will be partially saturated, right? Or unsaturated. And below the groundwater table, it's fully saturated. But the location of groundwater table is very important to determine the effective stress or the stress in the soil, right? Because it will change the total density and the saturated density. So fluctuation, but the groundwater table can fluctuate depending on the season. So in the rainy season, the groundwater table can rise up, and in the dry season, it can go down. So fluctuation is there, but it's not like really like dynamic fluctuation. The time scale of the groundwater table will be at the scale of several months. Yeah. So then, so above the groundwater table, what will be the degree of saturation? And will you have the water saturation difference with the depth? You can think of the capillarity. Capillarity is that the phenomena that the small pore sucks the water up. So, for example, if you have like water in a cup, in a container, and if you put this paper towel in there, then this paper towel will suck the water up, right? And the water will go up to wet this paper towel, and this is called the capillarity. Right? So this is the mud, right? The bay mud, and the groundwater table is at the same elevation with the ground surface. And if you dump the dry soil on that mud for reclamation, maybe you are building a pavement or road or asphalt, then you have to pour the soil and compact it, right, to be flat. Then this compacted soil will suck the water up from the subbase below the underlying soil layer. So then how much the water can go up? That will be the main question that we're gonna talk about in this later lecture. So let's look at the capillarity in soil first. So when you have a fully saturated soil, like you remember this kind of a picture, then it is fully saturated, and void will be all filled with water, right? So there will be no air. But as you dry out, water will evaporate, so then water will find a corner to minimize their surface area, right? So then it will become like this, and it will form a meniscus between the water and air and develop a surface tension because of the pressure difference. If you remember the high school physics or the high school chemistry, the water molecule here, H2O, and water molecule here, H2O, and here's the air, it will have different potential, or you will say the energy state. these are all surrounded by water molecule. So this water molecule is more stabilized. It will have a lower energy state than the one in here, because there's some force, unstable force, because of the air molecule will have a different fraction or the mass with the water. Some maybe physical chemical characteristic will be different. So then, because of this high energy state at the surface, the water molecule at the surface, they want to minimize this surface area. So when you have a droplet in the in the air, it forms the sphere, because the sphere makes the surface area the minimal. It's the same here. The water wants to find the corner, and they will form the meniscus, and this meniscus between the air and water will develop the surface tension. So you can even maybe, like if you have a paper clip like this, then if you have some grains on here, and if you add some water, if the water content is proper, then you can hold the soil grains, whatever the weight, with the surface tension. So keeping in that mind, we can use some tube analogy. And when we so let's go back here. The question was how far it can go up, right? Then for that, we can use the tube analogy here. The soil minerals are hydrophilic, so because it's made of silica, and it will make a concave meniscus, so that it will bring up the water. This is the air and this is the water, because of this small capillary diameter. And so then you can think of the capillary tube made of glass, and glass will be analogous to the soil mineral, and the size of this tube will be the analogy for the pore size or the void size. And as the capillary tube diameter decreases, it will bring up the water higher and higher, right? So then if we have the height, let me just black one here, capillary water rise or capillary rise height is hc, then from the force equilibrium, that's the weight of the water that brought up, that has risen, and the surface tension force that's bringing up that amount of the water will be equilibrated. So the force between the gravitational force and the surface tension will be the same. They will be balanced. So if the surface tension, we use the large T, capital T, and alpha is the contact angle between the water and air and the glass tube wall, then the weight of water that's forcing down, like bring it down in the direction of the gravitation, volume of water times water density times gravitation. So then hc times pi d square over 4 root of mg. On the other hand, the force bringing up this water mass will be T times pi d and cosine alpha. And we have to have a minus because the direction is different. So direction, the upward force is going up, so that's the negative sign, and downward is positive sign in this case. But that doesn't matter when you do the force balance here. So the summation of the force, the vertical force, will be 0 if you sum of F down and F up. Then you end up with this equation. Then if you solve it for hc, then 4t cosine alpha over rho w g d. This will be the final equation that you can use to compute the capillary HC. So this means that if you know the surface tension T between air and water, and if you know the contact angle alpha and the pore size, then you can compute the how much the water will rise, how high it will rise. And also you can compute the H or the UC, which is the capillary pressure, by using this capillary rise. And as we know the water height by this much, then if you plot the pressure in terms of the height, then pressure will be at here will be 0, and as you go downward, it's gonna increase positively, right, because of the gravitation. And if you go upward this way, then it will go the other way because of the surface tension. So here we use the negative sign, here we use the positive sign. So because it's compression and this is the tension, or you can say this is a suction and this is the pressure. So then this much of the pressure will be, because it will have the same slope like this. So then you can just multiply the water density and the gravitation. So rho, dot, and G and HC will be the capillary pressure. Then this becomes cancelled. The rho W and G at the bottom will cancel, and the 4T cosine alpha over D. So think about the unit. The capillary rise is in length dimension, so it will be in meter, and pressure is in Pascal or kilopascal and megapascal. For clean glass, we normally assume the alpha, the contact angle, is close to 0. So here, this is close to 0. This angle alpha, so almost vertical. So then cosine alpha will approach to 1. So we can remove this cosine alpha term, and we can approximate this equation into this 2. Right? HC equals 40 over rho of GD, and UC is, you can multiply the rho W and G. So there was the tube analogy. Then let's use the real number. For 20 degrees Celsius, the surface tension of the water in the air, T, is 73 millinewton per meter. So which is, millinewton is 1,000th of it. So 73 times 10 to the negative 3 times Newton per meter, or 0.073 Newton per meter. So then if we put it in the equation, HC will be 4 times 73 10 to the negative 3 Newton per meter over 1,000 kilogram per cubic meter times 9.8 meter per sec square times T. So then if you compute this one, this is Newton, so Newton will be cancel out. 2.98 10 to the negative 5 meter square over D. So then just you can approximate, this becomes 3 10 to the negative 5 meter square over D. So you don't have to use this equation, but this kind of shows that the capillary rise is inversely proportional to the diameter of the tube, right? The capillary tube. And here, if you use the D in length dimension meter, then meter square over meter will become the meter. So in the end, the length, the HC will be in the meter dimension or the length dimension. If you look at the textbook, actually it shows that the HC is 0.03 over D, and it doesn't show any unit, but it recommends to use the D in millimeter, and then you end up having the HC in meter dimension. But this is quite confusing, so I don't recommend to use this equation. I'll just use the this equation. I'll just use this equation or this equation. you can assume the alpha is 1. Alpha is 0, sorry. Because that's more convenient and it won't be confusing. Anyway, if you just follow the same rule and if you get the capillary pressure in the same way, then also it end up with this equation 0.3 over d Newton per meter. So if you put the d, if for example the pore size or the tube diameter is 1 meter, then 0.3 Newton per square meter. So that's gonna be 0.3 Pascal. And you can practice with this example. We're gonna actually solve it together in the lecture. And there are some empirical equation, empirical relation, because in the real soil or in natural soil, pore size is not just uniform, right? So just like the particle size distribution, you have a range of pore size, and it gives you the pore size distribution. So you have this kind of a distribution for the pore size. Then what will be the representative pore size to estimate the capillary rise, HC? So then let's think about these two soil. Let's say that this is the soil A and this is the soil B. Then particle size distribution will be what? A is quite uniform, so this will be the A. And the B has large particle and the small particle. So B will be maybe like this. Huh? So this will be the B. When you look at the pore size, this one is much smaller than this one. So in terms of the pore size, A is larger than the B. So then capillary rise will be higher in the soil B. So, and from this equation, from these two extreme cases, you can see that the small particle that's filling the large void determines the actual or the effective pore size. So the particle of fine fraction is critical, and it determines the effective pore size, which is dE. On the other hand, so how can we then determine the effective pore size? Let's think about different case here. So we have a soil A that has uniform size with some small particle like this one. And this one is what? Soil B. It has the same fraction, the small fraction, a small particle, the small particles with the same diameter with A, but it also have a large particle like this. So when you plot the particle size distribution, you have this one for the soil A and this one for the soil B. So it kind of shares the particle in here, but B has the larger particles too. Then when you look at the pore size, does it seem quite different or very similar? Because the small particles are the same, that's filling the large void. The pore size here is not that very different. Huh? So we can say that the pore size of soil A are pretty similar to that of the soil B. So that's why we use the small particle size to estimate the effective pore size. Especially for that, we use the D10. And we usually use empirically effective grain size D10 to determine the effective pore size dE. and you can use this equation. TE, the effective pore size, TE is 20% of D10. So 0.2 times D10. And then you can plug this one for T, right, rho of G and TE here, right? You can replace it here. So 4T rho of G 0.2 D10. So this is the one empirical relation that people widely use to estimate the effective pore size and to estimate the capillary rise and capillary pressure. Okay, then the second mostly wide one is the empirical relation by Tae-Hyuk et al. And here HC in meter is C over E D10. And here you can see the D10 is in meter, which is also the effective grain diameter, right? Effective grain diameter. And E is the void ratio, and C is just coefficient that ranges from 0.01 to 0.05. Generally 0.03 is used. So you can directly use this equation. So here we've seen the two empirical relations that we use the where is it? Effective pore size, and for that we use the effective grain size D10 to estimate the effective pore size and estimate the capillary rise using this theoretical equation. Or you can use empirical relation by the Tae-Hyuk and his co-worker using this equation. Okay, thank you.